Previously, we learned that the rate of any chemical reaction is equal to the rate constant times the concentration of reactants in some way. And as we said before, we're going to explore this rate law in a lot more detail in subsequent lectures. In this video, we're going to focus in on this K value, so our rate constant. And we said before that this rate constant can be calculated and understood using the Arrhenius equation, which says that the rate constant is equal to this pre-exponential factor times e to the minus activation energy over RT. So this rate constant is dependent on the activation energy, it's dependent on the temperature, and it's also dependent upon this pre-exponential factor, which we said before has to do with the orientation effects, right? So the orientation effects that we discussed in collision theory. These two terms have an awful lot to do with the likelihood that a molecule will have enough energy to actually react from a reactant to a product. Okay, so let's focus in on each of these two terms here again. So as we just mentioned, the pre-exponential factor, or the Arrhenius constant, is specific for a reaction, and it has to do with the orientation of a molecule. So it has to do with the likelihood that when molecules collide, that they collide with the proper orientation. Okay, this entire term here, this exponential term, e to the minus activation energy over RT, we're going to give this the symbol F. And it tells us about the percent of molecules that have enough energy to actually overcome the activation barrier. Okay, so this will always be in decimal form, and it'll be somewhere between 0 and 1. In theory, it will never get to 0, and it'll never get to 1, but it'll be somewhere between. So that decimal is the decimal form of the percentage of the molecules that have enough energy to react. Okay, so the beauty of this equation is that if you know the Arrhenius constant, the activation energy, and the temperature, then you can calculate the rate constant, right? And it kind of puts all of these things into relatable forms. All right, so let's explore this a little bit more. Okay, so if we apply the rules of natural log, so if we start with this Arrhenius equation, and we take the natural log of both sides, so I'm going to move down here now. All right, so if I take the natural log of both sides, so I have the natural log of the rate constant equals, so in this case we can use the rules of natural logs to separate the a term from the other exponential term. So this is the natural log of a plus negative EA over RT. Or we can rearrange this to be the natural log of K equals negative EA over R times 1 over T plus the natural log of A. So the reason that we do this is that it puts this equation, it puts the Arrhenius equation into a linear relationship where the natural log of K is our Y term. This minus EA over R is M. 1 over temperature is our X term, and the natural log of A is our y-intercept. So we have a y equals mx plus b situation here, which means that if we plot the natural log of k on the y-axis, and on our x-axis we plot 1 over temperature, then this should be a perfectly linear relationship. Okay, and this y-intercept right here, right? So where the line intercepts the y-axis, this is the natural log of the pre-exponential factor. And the slope of this line then is equal to the negative activation energy over r. Right? So if you're able to measure the natural log of this equilibrium constant at two different temperatures, right? So if you can measure the rate constant at two temperatures, then we're actually able to determine the Arrhenius constant and the activation energy. So here we have 1 over T2 we have 1 over T1. We have the natural log of this corresponds to K2, and this is our natural log of K1. So we have a rate constant at two different temperatures. Each of them fall on this straight line. So if we can measure two rate constants, so K1 and K2, at two different temperatures, T1 and T2, then from this relationship we're able to actually calculate the activation energy and the pre-exponential factor. Okay, so what I'm going to do now is go ahead and just do a little bit of algebra to put this into a more usable form. Okay, we know the slope of the line here is minus EA over R. Right? Anytime you have slope, it's rise over run. So our rise here, right? So we're going from K1 to K2. So our rise is the natural log of K2 minus the natural log of K1 over 1 over T2 minus 1 over T1. We can rearrange this now, right? So I'm going to take this whole denominator term and move it over here. So I'm going to take both sides times this. I end up with the natural log of K2 minus the natural log of K1 equal to minus EA over R times 1 over T2 minus 1 over T1. And now one more step using the rules of natural logs. This whole term becomes the natural log of K2 over K1. So just a little bit easier format to put it into, equals minus EA over R times 1 over T2 minus 1 over T1. Right? So this is the form of the Arrhenius equation that's really useful to actually help us calculate the activation energy. So if we're able to measure our rate constants at our two temperatures, right? So if we know two rate constants at two temperatures, then we can use this equation to calculate the activation energy. And if we know the activation energy, then we can use the other form of the Arrhenius equation, right? So we're going to know K, we know A, we know the activation energy now, we know R, and this is the temperature that corresponds with this rate constant. So the only variable here is the pre-exponential factor, so we can determine A. So these two forms of the Arrhenius equation collectively are really, really useful because they allow us to calculate the activation energy and the pre-exponential factor using experimental data. And in the next video, we'll actually explore some of these problems and work through them together.